volume by cylindrical shells. I wanted to give you a picture of a graph that we will start with. All right. This is y equal to x times sine of x cubed. And this graph just comes up like this. And then it goes like this, and it keeps going like this. But it intercepts here, everyone, on the x-axis. Some of you probably already know. Isn't the sine of pi equal to 0? You all agree sine of pi is 0? If you're curious what that number is right there. But it's being presented to you. I didn't want you to think you had to go and solve it right now. I know there's other times left to do that. And since the sine of pi is 0, everyone, the cubit of pi cubed would make this right here be what? Pi, and sine of pi is what? 0. I just want to point that out. This is the equation, y equal to x sine of x cubed. It keeps going. It keeps going. If you want to explore with technology, it comes down here and then it keeps going like this. Well, let's talk about taking the region bounded by this curve, all right, and the line y equals 0. So let's shade that right now. Can you shade the bounded region? And then I'm going to tell you which axis will revolve this around. Take the bounded region by y equals x sine of x cubed, that's that curve, and the line y equals 0. And this is y equals 0, right? So hey, let's shade here. So there's the bounded region. Let's find this. Let's find the volume of the bounded region. Well, I'll put solid generated. Find the volume of the solid that is generated by revolving that bounded region that we just mentioned about the y-axis. Okay. And this is just a good problem to present to give us an idea that, hey, maybe there's a better way to approach this problem than section 6.2. Maybe there's a better way than section 6.2 to approach this. Washer method. First of all, if we do the washer method, revolved around the y-axis, it would be very challenging to solve for what letter? X. Do you all agree? That would be one of the things we'd have to do. If we want to use the washer method, revolve this around the y-axis, then we know you solve for x in the equation at some point. And you notice that would be challenging? Second of all, if you look at this picture and you're thinking washer method, this would be weird how you did like outer minus inner. Isn't it the same function here? In terms of this getting revolved around here. But when we are going to roll this right around the y-axis, here I'll make sure this is nice and straight up and down. But we'll use a different technique. We're going to use a technique presented in section 6.3, the cylindrical shells method. Okay, so this is volume by cylindrical shells. So let's start out with just one cylindrical shell. All right, I'm going to take this piece of paper here. Here I'm going to cup it. I mean, that's a cylindrical shell right there, huh? Just like that, that'll work. There's some cylindrical shell like this. It's a cylinder, right? And we'll just call this a shell. We're going to sum a bunch of these. And it won't be challenging to find the volume of that region, the solid of that that's generated by revolving that region about the y-axis. But the first thing we have to do is use geometry and figure out, well, how do we get the surface area of some cylinder like this, of a cylindrical shell? How do we find the surface area of this? So, well, that forms a circle, right? What's the circumference of a circle? Brilliant, 2 pi r, is that one agree? So we're forming actually right now, and we're just discovering, we're developing what? We're going from memory. if you recall, what is the surface area of some cylindrical shell like this? Well, the circumference would be 2 pi r here, right? But then I'd have to multiply the 2 pi r times the what?
Height.
The height. And everyone, that is it. That is the surface area of some shell. Well, I'm going to write that down. Let's put it over here. The surface area. I'm not talking about the top or bottom if we put lids, right? Just that lateral portion that we had would be 2 times pi times r. That was that circumference. And then I heard also times the what?
Height.
Times the height. Well, what we'll do is, let's think about here. I'm going to build one cylindrical shell. We're going to think about how we can just sum up an infinite amount of cylindrical shells to come up with the answer. And you know, we do that by integral, right? Elongated s. So let's just look at one shell. When if this got revolved around the y-axis, it doesn't have to be perfect in your notes. What would it look like? So when this would come what? Whoop, whoop. So this would just keep, it would reflect and do something like this, wouldn't it? Like that. Make sure that's not right. All right, there we go. Something like this. This would come around here like that, and around here like that, around here like that, around here. Whoop, whoop, whoop. And we're revolving all this around the what? So have a nice big, just like that. So when we're going to build one cylindrical shell and focus on it, okay? How about right here? That would reflect right here. Just like I had before. And it's just a shell like this, okay? So I will put it like a little circle here just to say I know be the top. This is one of the infinite amount of shells that we will sum up. So let's talk about the volume of that one shell, right? Well, the volume, oh, excuse me, not the volume of that, but just the area. And then we'll sum up the area of all these cylindrical shells. We'll sum up an infinite amount of cylindrical shells areas. What's the area of that one shell? All right, well, it would be, area would equal, let me put it down again, 2 times pi times radius times height, right? But let's write it in terms of this function. So when for the word radius, 2 pi, what are we going to put for the radius? We've got to look at this image carefully. All right. This is the curve y equal to x sine of x cubed. We know that. Does anybody know what I can call that radius? It should be something simple because it's coming from the origin out this distance along the x-axis. What letter? It's just x. Outstanding. So we're going to call the radius just the letter x. You say, are we always going to do that? Sure. If we're revolving it around the y-axis. That'll be our radius of that shell. You all agree? From here, center out would be the distance x. But we need now something for the height. And we had 2 pi radius, that's x. Okay, your x. What's the height then? What would be the height of this in terms of this equation? What's that height right there? Well, we need to know what that function is. What's the function? X times what? Sine of x cubed? And wouldn't that represent the height at any value of x? So for the height, I'm going to put the actual function of y. I mean, you could start with this. Let's start there. Keep it simple. Radius is x, height is y. Okay, but what can I substitute for the y? 2 pi x, and then this y gets substituted by the equation what? X times sine of x cubed. Cool. And what we can do is put an integral symbol now and say sum up all these cylindrical shells. One here, 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 and all the way down. I'll say let's go from A to B. 2 times pi times x times, just put the function in there, dx. This will be the formula if it's revolved around which axis?
Y.
The y-axis. So this is the first thing, and we'll write this down again for this problem. We discovered that, but be careful. This is different from washer method. In washer method, when it got revolved around the y-axis, we had everything in dy, right? True? By the cylindrical shells method, if you're revolving about the y-axis, everything is in terms of what letter? Dx. And then these values will be x values. These limits here will be x. I didn't want that to trick you, but that's what happens with cylindrical shells.
Can you pull 2 pi out to the front or not?
It's a great idea. I want someone to rewrite this. He goes, why don't you put the 2 and the pi out in front? And this will just be x times what? F of x dx. And then just so you know, it's like sometimes you go, I'm going to have a hard time memorizing this. As long as you know this, you know that's that variable x, true? And then the height is just the what? The function, f of x. Radius was x, function was the height, h of x. So I can even draw some arrows here. This was the what? That was the radius, and this was the height. We're just summing a bunch of these shells. How many? An infinite amount. All the way from here, and then we're going to stop there. And we will accumulate all this to find the volume. Pretty cool method, huh? And this is helpful because the washer method would have been very, very challenging in this scenario. Hey, by the way, on that note, can you tell me what would be the formula that's revolved about the other axis, the x-axis? What's the formula? If it's revolved about the x-axis. All right? I think it's a good idea. Factor out the 2 pi. Put that out in front. A to B, what letter? Y. F of Y. And then lastly? And then we'll work this problem together. That would find the volume by cylindrical shells if that solid region you're talking about is going to be revolved about the x-axis. Just be careful, as I was saying, be careful, because wasn't this a little bit different from the washer method? Washer method is wonderful, it's outstanding, but there's a few instances like this example where it would be very challenging. And that's why we teach section 6.3. That's why I instruct. All right, well, let's work this problem together. Okay, I'm going to set it up. The limits of integration, everyone. This is getting revolved about the y-axis. I'm using cylindrical shells, dx. I'll put the 2 pi out in front. Your suggestion, I like that. What's the limits? These were given. Can everyone see the x values? This was 0. And this was the cube root of pi. All right. If anybody wants to know what problem from the textbook this is like number 2 from section 6.3. It's like number 2. And the same thing, they drew a picture of the graph. All right, now what do I put down? Well, the radius. And I really do, I don't know about you, I just do this from, I'm like, well, what's the surface area? 2 pi r times height. That's the radius. And the height is the function, which was what? X times sine of?
X cubed.
X cubed. Hey, be careful, this is just a warning. I've seen students do this on tests over the years. They're about to work the problem, and for some reason it slips their mind, they forget to put this x here. Isn't this automatic? They just think, oh, integral of f of x. It just slips. So if you ran that jam, you'll be looking at this going, man, I don't have an integral technique to do this. But now we have that x with the other function, there's a way we can solve this. We've all come from Calculus 1. There's an integral technique. Very popular, allows us to solve this problem and other problems as well in our course. By the way, what is x times x? X squared. Sine of x cubed. And some people might just need a little, review of this. What's the method that allows us to integrate this? I heard it. What was it again? He calls it a U sub. It's the substitution rule. So when we got to find this integral right now, we're trying to find the antiderivative of x squared sine of x cubed. He says you have to use the substitution rule. he called it a u sub because a lot of times we just write u equals something. So I'm going to go off to the side here and perform a u sub so we can solve this. Alright, so I'm going to do a u sub. Let u equal to, anybody know?
X cubed.
Brilliant. They went for the higher power. So if you need a little review on this, we looked at x squared, x cubed. You notice this was higher than this by one integer. And that's where they went for it. Not the sign of x cubed, just the simple x cubed. That's step one. Step two, differentiate both sides with respect to x. Okay, du. And this will be 3x squared dx. I'm going to do one more step, everyone, because my goal is to get rid of this x squared dx. So I'm going to divide that 3 on both sides. So I get 1/3 of a du equals x squared dx. And now it's time to substitute. Now I did this off to the side, right? And, oh, there's people in this class, I know it, they're like, I can do that in my head. Like, they'll automatically do the u sub 3 steps in their head, and that's cool. But there's nothing wrong with us writing this down. True? Off to the side. Okay, let's start with this. What does this replace?
X cubed.
All right, that x cubed gets replaced with a u, but the sin is going to stay, right? Keep that sin there, the sign. What replaces the x squared dx?
1/3.
The 1/3 du. So when I'm going to go up here and actually go in here with my chalk, say you're gone, but it gets replaced with a 1/3 du, right? You're like, here, put in this, you're going to put a 1/3, and you're going to change this to a du. Now this looks all sloppy, so I'm going to clean this up, right? I got things crossed out and stuff. What do I have left right now? I have a 2 pi. I have a 1/3. Everyone okay if I put the 1/3 with the 2 pi? I'm going to do that, isn't it? 1/3 times 2 pi over 3, out in front of the integral. Still got this sin left, and then what letters here? Boy, did this get nice. So does everyone see this? This is by the substitution method. And if you need, like, in a class, you're like, I need to brush up on that. Oh, I can give you my videos. I can just give you some, some supportive stuff just to get that, freshen up on that, some practice problems.
So the 1/3, because it's a constant, we just took it out of the integral?
Yes,
Multiply.
because it was a constant. You could have left it there, but I was like, hey, we got another constant. Might as well put it with the 2 pi out in front of the integral.
Because if we take the integral of constant, then it will be 1/3 x, and we would just be doing more work, right?
That's right. Now here's something else I want to point out. I mean, if you need a little review with u subs, I changed everything from x's to what letter.
Yes.
So do you notice, just being a math teacher, I didn't write these two same numbers down? Because these were actually what values? X values. These are now what values? They're u values. Now if you want to go find them, you can. You can figure out what they are. There's the little conversion. But I figure, how about just leave it blank. I'll finish this out and resubstitute, get everything back in x's, and then use these two numbers. That's what I did. Okay? But some students like to change those limits of integration to u's. Anybody in here? I'm going to look. It's not the way he does it. There's about 2 in here. They actually like to do that. So if you're curious, you're like, well, how do you change this? Oh, it's right here. So that's an x value, and that's an x value. That's x, and that's x. What is 0 cubed? 0. What is the cube root of pi cubed? Pi. So if you want to know how to do it, it's not too hard, but you have to look at what you used in terms of what you set u equal to. Cool. But a lot of times I just leave these blank. Because I'm like, hey, I'll just keep going. I put everything in terms of x. I put it back in x, and I use the original limits of integration. All right, now, we were talking about this morning. Hey, what's the name?
No.
Oh, no. So here it is. Sometimes we get confused. The integral of a sine is a cosine, is a negative cosine. Just a mnemonic device. SC, SC, S. This way is derivatives, but this way is antiderivatives. This would be integrals. And it's just a mnemonic device that we can say, oh, I don't want to confuse a positive and negative. So the integral of sine is a negative cosine or cosine?
Negative cosine.
Negative cosine. Is that one agree? Right there. What's the integral of an s? It turns into a negative c. This way is integrals. So the integral of sine is negative cosine. If that helps. True? Because I know, it's probably happened before. You're like, oh man, I lost points. I put the integral of sine as cosine. Right? You're like, no, the derivative of sine of x is cosine of x. But the integral of sine of x is negative cosine. So I'm going to put that here. I'll put it with the 2 pi over 3. Almost done, everyone. I get cosine of u, and I put my 2 limits, right? Now, what are the 2 limits? 0 and what? Pi. If you didn't change them to u's, could I reuse the original x's?
No.
0 to pi. I would have just resubstituted. And right here, I would have had, what was u equal to?
X cubed.
And I put it back in. So you can use either one of these, and we put the proper limits. This was 0 to what? Cube root of pi. Which one do you want to use? I had about 2 hands show they like to do this. I'll be honest, most students do this, so they don't get confused. They just use the original what? Just remember, you got to resubstitute, true? So I'm going to use that just because I notice when I'm grading, most students like to do this.
Why did the 2 pi to the third change to negative?
Oh, because of the integral of sine is a negative cosine, right? And I just stuck it way in the front. But hey, we're finding volume. Do you agree our final answer should be positive?
Yeah.
Volume can't be negative, can it? So I do want to point out, I know that's negative, but watch what you get for your final answer. It should come out positive. You probably would have caught that. If you and I forgot that, we came down the end, probably got a negative answer and said, something's up. We're going to look back to see what we messed up. All right, well, I'm going to use this one. What's negative 2 pi over 3 times, and all I'm going to do, everyone, I'm just going to do cosine of this minus cosine of that. Okay? What's the cosine of cube root of pi cubed? That's a cosine of pi, right? Cool. And people know what that is. Then I would subtract, and I'd get the cosine of 0. Now, what's this number? Negative 1. What's this number? 1. What's the final answer? Oh, it's positive. What's a negative 2? Is that 4 pi over 3? Good job with this. Any questions on that? Step away. Yeah.
Got to review these, the cosine
Oh, okay.
sheets.
Excellent. Doing a super job with this stuff. Hey, one more. I think it's always good to take a problem we did yesterday from 6.2 that we just found easier with the washer method and let students try to approach it with the cylindrical shell method, just in case they wanted to do it, right? Like if you're wondering my preference, I like washer method, but you notice in this problem, it was what? It was just this was way easier to deal with by using cylindrical shells. Nice. Hey, can I erase this? Yeah. Ooh. Great job with that, everyone. All right, I'm gonna pick something from yesterday. How about, or something very similar to yesterday. How about this? Y equals x. Nothing too crazy. And y equals x squared. You know, just wondering, maybe I should draw it bigger since we're going to make these shells.
Make it a little bit bigger.
Throughout the year. Y equals x. Y equals x squared. And everyone, we're going to revolve this region right here, bounded by y equals x and y equals x squared, about the y-axis. Well, can we just start about the setup? If we use the washer method, let's see what we get. What will we do by the washer method? And we'll just set this thing up. X-axis, y-axis. This thing would go what? If we use the washer method, would this go? Integral pi dx or dy? See, when we can do a problem both ways, then you're a master. That's why I wanted to kind of finish up 6.3 with a problem like this. Let's set this problem up both ways. Washer method, going around the y-axis, the volume of the solid region, volume of the solid generated by revolving this region about the y-axis. Outstanding, you said dy. Okay, because we're using the washer method. And then, what's the setup? What goes here? Pi r squared minus pi r squared, right? And then when we will finish filling all this stuff in, okay? Don't worry, we will. I just want you to compare this to cylindrical shells. We're like, okay, cylindrical shells, what do we factor out in front instead of just a pi? 2 pi. But when it got revolved around the y-axis, what did we do? Dx. And here we just wrote the letter x. And then we put the function, right? Well, I'll just put a question mark here for now, because you and I might be kind of startled by this. How are we going to do that? Because how many functions you got? 2. So that's what we're talking about. Well, but let's start out with this. This, I think, to me, if you ask me, there might be a student in this class who prefers this. Seriously. Me, I'm like, I like washer method. I think it's pretty easy. I just got to do outer minus the what? Outer minus inner, and I got to solve for what letter? X, right? Because it's going around dy. Let's go around the y-axis. Which one's further away from the y-axis? X squared. Okay, so this one's further away, but you got to solve for what letter? So what would x equal to? Square root of y? All right. Now, who is closer? The inner. But I need you to solve for x. What's x equal to? Oh, this was easy. It's just a what? Y. Where's Sean? Sean's theorem is, what if I had these mixed up? What could I do? Put what? Absolute value bars here, and I'd get it. And I never wrote down the limits of integration. These have to be y values. So what are these two y values? Pretty simple. What are they? 0, 1. How about this, though? I was wondering if you can help me. So let's build one shell. I think it helps when you just actually draw one of the shells. So I'm going here, and what would the reflection look like over here? The reflection would kind of come up like this. This would be underneath, right? There's the reflection. Good enough, right? Let's build one shell. On one shell, I'm like, okay, I go out like a distance x, go up, stop, come back over here, come up. I'm building one shell, and I'll get out of the way. I don't want to be a wall to anybody. Here, I just built one shell, so you can kind of look at it. The radius is still what letter? This is still the radius, everyone. Don't be fooled. The radius is still what? X. It's still X. Cool? So that's what? That's nice. You go, why? Can you see it? What's that distance from there to there? We can call that the distance x. True? What's the limits for the x values? Because these have to be x values. So where did these two meet? An x equal to 0, and what was this x value here? So this is 0 to 1. This is looking pretty easy too. Maybe the only challenge, but I know you're going to come up with this, is determining what to put for f of x. Recall, this really represented the what? Right? The height. And if you could look in there and figure out a mathematical way to come up with an equation for that little height right there, then you got this section, you're pretty powerful. You understand cylindrical shells. So I'm going to change this f of x and say, what do we put here? This is going to be the height part. Does anybody in the class have an idea? Someone's going to come up with this. Ooh, how could I represent the height? Because we're all confused. There's a y equals x, and there's a y equals x squared, but that would be the height there. What do you do? X minus x squared. He took the difference of the two y's. Do you all agree? Something similar to what we did with area. To find that little distance right there, which would be the height of that cylindrical shell, he says you just take the difference between this and this. That's what I'm going to call my height. X minus the times squared, and this would work too. Both of these are equivalent. Both, you can check, we're not gonna solve them now, but you can check both of these. Do all the math, you get the same mathematical answer.
So we wouldn't have to square the equation like we would in the Walker method?
That's right. And I know they can be confusing. That's probably why you'll find there's some colleges in Calc 2, they go, all right, let's just skip cylindrical shells. Students are gonna get confused, you know. It's only great for certain circumstances. Washer methods are great everywhere, you know. But you're right, you gotta be careful because we thought of what? Pi r squared minus pi r squared. We kept making all these washers. The thing with the cylindrical shell was, it was a bunch of areas. It was a bunch of 2 pi r h's. 2 pi r h's that we summed up. And so there's no squaring going on in terms of that, except when we know writing down the function equation, that's it. But I want both of these, you can distribute that, solve it, you can square those, solve it, you get the math, they both be equivalent.
I want to test, do we get to choose or like in the description it's going to tell us to use?
Great question. For me, like, I usually let you choose, right? If I say, all right, I want you to do this one problem by the washer method, I'll be doing that just to assess that the students know how to do that. I do want to point out, that was a good question, because at least from section 6.3, you remember the problem previous to this? At least for me, I will definitely want to present a problem that's just like that scenario. And want to see, I'll say, what would be the most, what would be the best way to attack this problem? Because definitely washer method would be very challenging on that last scenario. Cool. So let me just repeat that, everyone, so you're curious. I do like to put a problem like that last one that I did. Previous to this, I had that what? It was just something that went up like this, it came out like this. We're like, man, with this, it was hard to solve for the letter X. Washer method would be very challenging, but by cylindrical shells, by that method, it would be not hard at all. We just had to do a substitution rule.
Can you just explain why the cylinder doesn't start on the x-axis?
Great question. So when we had to build all these shells to sum them up, because what we're going to do is we're going to in the end, generate a three-dimensional solid. So if you start right here to make the first cylinder, I see that this curve is right here at the origin. So you're like, okay, I can't even move. But then you might, for your next one, you might put one right here. When I go for my radius, it's always going to be this outer curve that's furthest away. For the height, I'm always going to build like go up. But watch me keep shading this in. You're going to do that one, sum it with this one, then sum it with this one. I keep having to lift it up a little bit because I go straight out and then up. And I'll keep going, keep going, keep going. See how I keep lifting it up to get the, and then I build all these cylinders. I'd sum the areas of all these cylindrical shells. So that's what's happening there. So I know it can be confusing when there's two of them. But when you come to that radius, you go, let me just shoot out, here I'll build another one. Like, shoot out all the way just to see what would be the radius of that shell. Right? Then you go like, right? But still, I do want to point out, is the height all the way down? The height's only going to be the difference between this and this. So that's why I didn't shoot all the way down like before.